So today's session is essentially a revision session on binomial theorem. Now, the first sum that we'll be concentrating on is using binomial theorem, find the value of 99 whole to the power 4. Now, of course, you can multiply 99 4 times, but if you're anything like me, then to you, addition and subtraction is easier than multiplication, no matter how complicated addition and subtraction is. So what we'll essentially do is we'll convert this multiplication based sum into a sum which consists of only additions and subtractions. And we'll of course use binomial theorem to do that sum. So the first step is we'll split up 99 into 100 minus 1. So 99 whole to the power 4 can be expressed as 100 minus 1 to the power 4. Next, what we'll do is, if you remember the binomial theorem exercise that we had done, we can express this as a minus x whole to the power 4. So that is exactly what we'll do. So a becomes 100 and x becomes 1. So if a minus x whole to the power 4, the expansion was a to the power 4 minus 4c1 a cube into x plus 4c2 a square into x square minus 4c3 a into x cube plus x to the power 4. That was the original binomial expansion of a minus x whole to the power 4. So obviously we'll be replacing a with 100 and x with 1. So we get 100 to the power 4 minus 4c1 100 cube into 1 plus 4c2 into 100 square into 1 square minus 4c3 into 100 into 1 cube plus 1 to the power 4. So that's the basic replacement. Now, obviously, very easy to find 100 to the power 4 and 100 cube and 100 square. So that's exactly what we'll do. And 4c2 is essentially 4. You can find that out by using NC1 or NCR rather is equal to n factorial by r factorial into n minus r factorial. So this expression we have discussed in our previous video. If you don't remember, you can always go back and check it out later. So we'll essentially use this relation and we find out the value of 4c1 to be 4. So that's 4c1 is 4 factorial by 1 factorial into 4 minus 1 factorial. So we are left with 4 factorial by 1 factorial is essentially 1. So we get 4 factorial by 3 factorial, and 4 factorial is actually 4 into 3 factorial. So the 3 factorial part gets cancelled and we have 4c1 equals 4. In the same way, we get 4c2 as 6, and since we know that NCR equals NCn minus r, using that expression, instead of even going to this expression of NCR equal to n factorial by r factorial into n minus r factorial, we can simply use the relation NCR equal to NCn minus r. So 4c3 is equal to 4c4 minus 1. So it becomes 4c3. So we can get 4c3 equal to 4c1, sorry. So we get 4c3 equals 4. 4c1 equal to 4c3 equal to 4. So we just replace these values. So we get 100 to the power 4 minus 4 times 100 cube. So that gives me this value. Then we have 4c2 into 100 square. So that's 6 into 100 square. And then we get 4 into 100 and then plus 1 to the power 4. So that's 1. So next we just simply do this addition subtraction calculation, which is obviously way easier than doing 99 whole to the power 4. And so that gives me the answer 96. Wait, let me just, yeah. So that's my answer, 9605961. Okay. So that's the first sum done. That was a relatively easy sum. It's just an application of binomial theorem. The next sum is if the term independent of x in the expansion of this big expression be 2268, find the value of k. So they essentially want us to find that particular value of x, that particular term in the expansion of this binomial expression which is independent of x. And they have said that that term which is independent of x has this value, that's 2268. So we'll go step by step. We'll first find out the term which is independent of x. So let's say we have a r plus 1th term which is independent of x. This is an assumption that we make. So let's say that we have the r plus 1th term of the expansion to be independent of x. And as per the sum, that r plus 1th term will be 2268. So we'll go to this part later. We'll first start with this independent of x part. So as we know, the t r plus 1 expression is ncr a to the power n minus r x to the power r. So that's like the first term to the power n minus r into the second term to the power r. So here essentially what we have done is we have taken it plus, so it's k by 3 x square plus minus 3 by 2x. So we have taken this entire term as x. So we get t r plus 1 equal to 9cr k by 3x square whole to the power 9 minus r, because it's here n is equal to 9, so we have 9 minus r, and it then we get we multiply it with my minus 3 by 2x whole to the power r. So that's my t r plus 1, which is my r plus 1th term of the expansion. Now what we do is, this, since they have told me that this term is essentially independent of x, we just simply take out the x parts from this entire expression. So we are left with ncr. If we take out this x part, then we are left with k by 3 whole to the power 9 minus r. So that's what I've written here. And then from this part, if we take out x from here, then we have minus 3 by 2 whole to the power r. So this part is what we are left with if we remove x. So what we are left with, x squared to the power 9 minus r, that's essentially x to the power 18 minus 2r. And if we again put x to the power minus 2r, then we can get a total exponential of x to the power 18 minus 3r. So 18 minus 2r from this portion and minus r from this portion. So we are left with x to the power 18 minus 3r. That should be the x, that should be the term of x, that the term that involves x in the r plus 1th term of the expansion. But they have said, and as per our assumption, this t plus tr plus 1th term is independent of x. So this 18 minus 3r should be 0. Only then can we say that the term will be independent of x, because if this exponential is 0, then the x term vanishes and we have it, we have the r plus 1th term to be independent of x. So what we do is we equate this exponent to 0. Yeah, t r plus 1 independent of x implies that 18 minus 3r equals 0. So that gives me the value of r to be 6. So essentially this tr plus 1 is essentially the t7th term, because if I put r equals 6 in this expression, I get t7. So we have under consideration the 7th term of the expansion. So yeah, that's what I've written, and I find that essentially t7 is 2268. Now I have the value of r and I have the value of n from the expansion itself, because the exponential here was 9, so the n value is 9, and we have the value of rn from here as it's 6. So we essentially have all the rules, and we can just find out ncr a to the power n minus r k to the power r, and since x value we found out to be independent, there's no question of x in this expression. So we just merely put the values and we equate it with 2268. And as you can see, this is a simple equation involving k. So if we solve it, we get k to the power 9 by 6. So it's k cube equals 64. And since k values, we are considering just real values. This is basically, it's better if you write it, because there may be non-real or imaginary terms as well. So it's better to write that since we are considering real values of k, we get k equals 4. So that's what we essentially were required to find. We were required to find the value of k, and we find the value of k to be 4. The next sum is, show that the coefficients of x to the power m and x to the power n are equal in the expansion of 1 plus x whole to the power m plus n. So for x1 plus x whole to the power m plus n, we can express the rth expression, or this should actually be tr plus 1. So we can express the r plus 1th term of the expansion as m plus n cr x to the power r, because the coefficient of, like, since it's 1, so any 1 to the power anything is 1 itself, so we can ignore this one part. So we get 1 m plus n cr x to the power r. So we have m plus n cr into x to the power r. Now they have told me that they have asked me to rather find the coefficients of x to the power m and x to the power n in the expansion of 1 plus x whole to the power m plus n. So you see, if we consider the term tr plus 1, then we get the exponential of x to be r. So again, there's a mistake here. Yeah, 2b plus 1 and it's 2b plus 1. But it doesn't exactly matter because the sum essentially remains the same. So if we consider the t plus 1th term, then the exponent of x is r. So whatever number, whatever term we take here, the exponent of x is that minus 1. So it's r plus 1 minus 1. So if we use induction or if we use basic, what should I say, intuition, then the t m plus 1 term will be m plus n c n x to the power m, and t n plus 1 is m plus n c n x to the power n. That's like the basic relation, and we have converted it to a term that we need, so that we essentially need x to the power n and x to the power n. So we have converted the expression that we know to an expression that we need. So we have adjusted our expressions accordingly. Now, hence, the coefficient of x to the power m in the expression will be m plus ncm, and the coefficient of x to the power n in the expansion will be m plus ncn. So the next step is essentially we need to show that this term itself, m plus ncm and m plus ncn are same. So that's what the sum boils down to. Now that is essentially a very easy stuff if you remember the relation that NC n minus r is NCR. So it's like the relation that we discussed in the first sum of this exercise. So m plus n, if I take m plus n as a single entity, then m plus n cm can be written as m plus nc m plus n minus n, because n gets cancelled. So we are left with m plus ncm. So this adjustment is possible. There's nothing wrong with this adjustment. Now, if I replace m plus n with some other value, let's say, what should I say? Let's say it's p, and let's replace this n with q. So it's like writing p, c, p minus q. Now, if NC n minus r is NCR, then P, C, P minus r will be PCR as well. So P, C, P minus q is P, C, q. So that should be m plus n, c, whatever has been deducted. So it's P, C, n. So it's m plus n, c, n. Now you see m plus ncm has been equated with m plus ncn. So essentially these two coefficients are the same, and that is what we had been asked. So the coefficients of x plus n and the coefficients of x to the power m and x to the power n are essentially equal in the expansion of 1 plus x whole to the power m plus n. So that is, this sum I find really interesting, and I have always enjoyed doing these kinds of sums. Binomial theorem has really interesting sums in its stock, and I find it's a relatively more interesting and a more intriguing chapter of mathematics. So yeah, that's the revision of the exercise. If you have any doubts regarding this chapter, feel free to